Welcome to our comprehensive guide on operating systems. Whether you're a student preparing for exams or someone curious about how your computer really works, this video will help you understand all the major topics, from OS fundamentals, processes, and memory management to advanced concepts like deadlocks and real-time systems. Let's dive into the world of operating systems. Module 1. Introduction to Operating Systems. First, what exactly is an operating system? An operating system is a software that acts as a bridge between the user and the computer hardware. Its main functions include managing hardware, running applications, handling input-output operations, and ensuring security. Now let's look at the objectives and characteristics of an OS. An operating system provides user convenience, system efficiency, and the ability to evolve. Important characteristics include multitasking, multi-user support, and resource management. Next, let's talk about the structure of an operating system. Most operating systems follow layered, monolithic, or microkernel architectures, depending on how components are organized. So, what are the main components of an OS? They include the kernel, file system, device drivers, user interface, and system libraries. Speaking of kernels, let's briefly explain the Unix kernel. The Unix kernel is the core part of the Unix OS. It manages processes, memory, file systems, and hardware communication. Module 2. Process Management. Let's start by defining a process. A process is a program in execution. Every process has its own memory space, process ID, and a data structure called the Process Control Block, or PCB. Now, what is a thread? A thread is the smallest unit of execution within a process. There are two types: user-level and kernel-level threads. User-level threads are managed by user programs, while kernel-level threads are managed by the OS. Let's compare them in detail. Moving forward, let's explore threading and multithreading. Multithreading allows a process to run multiple threads simultaneously, which improves efficiency and performance. We'll also compare various multithreading models, including many-to-one, one-to-one, and many-to-many. What's the difference between a process and a thread? A process is independent, with its own memory. Threads share the same memory and are lightweight compared to processes. Next, we discuss the process state model. A process typically moves through states like new, ready, running, waiting, and terminated. Now let's cover process scheduling algorithms, such as first come first serve, shortest job first, round robin, and priority scheduling. These are critical for efficient CPU usage. How do processes talk to each other? This is done through inter-process communication (IPC) mechanisms like pipes, shared memory, message passing, and semaphores. Finally, we revisit multithreading and its advantages, such as better CPU utilization and responsiveness. Module 3. Process Coordination. Let's begin with a key issue: deadlocks. A deadlock occurs when a group of processes are blocked, each waiting for a resource held by the other. We will discuss the 4 necessary conditions for a deadlock and how a resource allocation graph helps detect it. Next, we talk about deadlock avoidance and recovery strategies, including techniques like the banker's algorithm and process killing. What is a critical region? It's a part of code where shared resources are accessed. Synchronization is essential to avoid conflicts. We now explore semaphores, a synchronization tool. Using semaphores, we solve problems like the dining philosopher's problem efficiently. Finally, let's understand race conditions, where the system's output depends on the timing of threads, often leading to unpredictable behavior. Module 4. Memory Management. Let's begin with page replacement. This technique is used when a page needs to be swapped in and out of memory. We'll explore algorithms like FIFO, LRU, and optimal with examples. What is paging? It is a memory management scheme that eliminates external fragmentation. We'll explain how logical addresses are converted to physical addresses. Now, what is virtual memory? It allows execution of processes that may not be completely in memory. Advantages include multitasking and memory efficiency. Next, we examine memory fragmentation, both internal and external. We also cover segmentation, where memory is divided into variable-sized segments based on logical divisions like functions or arrays. Another topic is demand paging, where pages are loaded only when required, reducing memory usage. We'll discuss the hardware support needed for this too. Numerical section. 1. Page replacement. For the given reference string 1, 2, 3, 4, 2, 1, 5, 6, 2, 1, 2, 3, 7, 6, 3, 2, 1, 2, 3, 6. We'll calculate page faults using FIFO, optimal, and LRU with 4 frames. Similarly, for another reference string, 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2, 1, 2, 0, 1, 7, 0, 1. We analyze faults using all 3 algorithms again. 2. Memory allocation. With partition sizes 400, 180, 100, 300, and 45, we'll use first fit and best fit methods for memory requests of 95, 180, 285, 380, and 30. Module 5. Storage management. Let's discuss file allocation techniques, such as contiguous, linked, and indexed allocation, along with their pros and cons. What is RAID? RAID stands for Redundant Array of Independent Disks. We explain RAID levels 0 to 6, including mirroring, striping, and parity. Next is Direct Memory Access, or DMA, which allows devices to transfer data directly to memory without CPU involvement. What is disk scheduling? We'll explain algorithms like FCFS, SSTF, scan, and look, including numerical examples. Finally, we cover file attributes, file operations, and different file types. Module 6. Special topics in OS. We now explore the features of mobile and real-time operating systems. Mobile OS focuses on touch, connectivity, and battery efficiency, while real-time OS ensures timely task execution. We also look at the objectives and characteristics of modern OS, including network operating systems, which allow computers to communicate over networks. Let's explore the Android OS, its architecture, and how it handles apps and permissions. Next, we'll address design issues in mobile and real-time systems, such as power usage, latency, and resource constraints. We also touch on cloud operating systems, which manage distributed resources and provide scalable services. Lastly, what is an open-source operating system? It's software with publicly available source code, allowing customization and community contributions, Linux being the most popular example. Thanks for sticking with us through this deep dive into operating systems. If you found this helpful, like, share, and subscribe for more technical breakdowns and exam guides. Got a question or topic request? Drop it in the comments below. Until next time, keep learning, and keep exploring tech.